process heat transfer. In this lecture, I will mainly talk about the heat transfer by radiation and the wavelength of radiation. Then I will talk about the emissivity and black body radiations. Further, I will discuss the Stefan-Boltzmann law and Planck's law and the Wien's displacement law. At the end, I will discuss about the radiative heat transfer to opaque and semi-transparent materials. And finally, I will discuss about the combined heat transfer by all the modes of heat transfer such as conduction, convection and radiation. The introduction of radiation. Let us first of all discuss these two diagrams. First of all, consider a hot object that is suspended in the vacuum chamber whose walls are at room temperature, right, in this diagram. The hot object will eventually cool down and reach the thermal equilibrium with its surrounding. It will lose the heat until its temperature reaches the temperature of the walls of the chamber. Heat transfer between this object and the chamber could not have taken place by conduction or convection because these two mechanisms cannot occur in the vacuum. Therefore, the heat transfer must have occurred through another mechanism that involves the emission of the internal energy of the object, and this mechanism is known as radiation. Radiation differs from other two heat transfer mechanisms in that it does not require the presence of material medium to take place. In fact, energy transfer by the radiation is the fastest at the speed of light, and it differs no attenuation in a vacuum. The radiation heat transfer occurs in solids as well as in liquids and gases. In most practical application, all three modes of heat transfer occur simultaneously at varying degrees. But the heat transfer through an evacuated space can only occur by the radiation process. For example, the energy of the sun that reaches to the Earth's surface only by the radiation. You will recall that the heat transfer by the conduction or the convection takes place in the direction of decreasing temperature. What does it mean? It means that from a high temperature medium to a low temperature medium, the heat will transfer. It is interesting that the radiation heat transfer can occur between two bodies separated by the colder than both the bodies. For example, in this diagram, the radiation heat transfer will take place between these two objects. This is the person which has at the temperature of 30 degrees centigrade and the fire which is at 900 degrees centigrade. And there is a medium or the air in between these two objects which is at 5 degrees centigrade. So the radiation can take place between these two objects through this medium. For example, solar radiation reaches the surface of the earth after passing through the cold air layers at very high altitudes. The radiation absorbing surfaces inside a greenhouse reaches the high temperatures, even its plastic or the glass covers remains relatively cool. Now let's discuss about the wavelength of radiation. The theoretical foundation of radiation was established back in 1864 by a physicist that is called James Clerk Maxwell, who postulated that the accelerated charges or changing electric currents give rise to electric or magnetic fields. These rapidly moving fields are sometimes called electromagnetic waves or electromagnetic radiation. And they are represented by the energy emitted by the matter as a result of the changes in the electronic configuration of atoms or molecules. In 1887, Hertz, which was a scientist, experimentally demonstrated the existence of such waves. Electromagnetic waves transport energy just like other waves, and all the electromagnetic waves travel at the speed of light in the vacuum, and we all know that the speed of light is 3 × 10⁻⁸ meter per second. Electromagnetic waves are characterized by their frequency, which is represented by this mu, and the wavelength, which is represented by this lambda, and these two properties are related by this expression. This wavelength and frequency are inversely proportional to each other. When we replace the inverse proportionality sign, we will have a constant, which this constant is known as the speed of propagation of a wave in that medium. So commonly used units for the wavelength is the micrometer or the nanometers. Unlike the wavelength, the speed of propagation, and the frequency of electromagnetic waves depends only on the source and independent to the medium through which the waves travel. The frequency, which is also known as the number of oscillations per second of an electromagnetic wave, can ranges from less than a million hertz to a septillion hertz or higher, depending upon the source. So the wavelength and the frequency of electromagnetic radiations are inversely proportional to each other. So it has been proven that the electromagnetic radiation, as the propagation of or the collection of discrete packets of energy, which is sometimes called the photons or the quanta, proposed by the Max Planck in 1900 in his quantum theory. In his view, that each photon of frequency nu is considered to have an energy of E, and the Max Planck has proposed this expression in which the energy of the photon is inversely proportional to the wavelength. And here we have two constants, that one is known as the Planck's constant, and it has a value of 6.6256 into 10 raised to the power minus 34 joule seconds, and C, which is known as the speed of light, and it is also known as constant. So this expression shows that if the radiation has the shorter wavelength, so according to the inversely proportional relationship, the radiation will have the maximum energy. Or in the second scenario, if the radiation has the longer wavelength, so it will have the small energy. Now let's discuss about the thermal radiations. Although all the electromagnetic waves have the same general features, the waves of different wavelength having different behavior. The electromagnetic radiations encountered in practice covers a wide range of wavelengths, varying from 10 raised to the power minus 10 micrometers for the cosmic rays to the range of 10 raised to the power 10 micrometers for electrical power waves. So this is called the electromagnetic spectrum, which also includes the gamma rays and radio waves, microwaves, and visible rays, ultraviolet rays. And it can be seen that this electromagnetic spectrum has a range for different wavelength, has a range of wavelength for different radiations, such as the microwaves lies in the range of 10 raised to the power 2 to the 10 raised to the power 5, and the thermal radiations that we are going to discuss in this topic ranges from 10 raised to the power minus 1, which means 0.1, to the 100, 10 raised to the power 2, which means 100 micrometers. So the thermal radiations that we are going to discuss in this lecture lies in the range of this electromagnetic spectrum from 0.1 micrometer to 100 micrometers. So different types of electromagnetic radiations are produced through various mechanisms. For example, these are the gamma rays, and which are basically produced by the nuclear reactions, and these are the X-rays, which are produced by the bombardment of metals with high energy electrons. Similarly, these are microwaves, which are produced by the special type of electron tubes such as klystron and magnetrons, and radio waves are produced by the excitement of some crystals by the flow of alternating currents through electric conductors. So the short wavelength gamma rays and the X-rays are primarily of concern to the nuclear engineers, while the long wavelength microwaves and the radio waves are of concern to the electrical engineers. The type of electromagnetic radiation that is pertinent to the heat transfer is the thermal radiation, emitted as a result of energy transition of molecules, atoms and electrons of a substance. Temperature, which is actually a measure of strength of these activities at microscopic level, and the rate of thermal radiation emission increases with increasing temperature above absolute zero. Everything around us, such as walls, furnitures, and our friends, constantly emits or absorb radiation. As you can see in this house, hypothetical house, if there is some furniture, plants and walls, and people are sitting inside the house, so everything is emitting some sort of thermal radiation or absorbing thermal radiations. So the thermal radiation is defined as the portion of electromagnetic spectrum that extends from 0.1 to 100 micrometers. Since the radiation emitted by the bodies due to their temperature falls almost entirely into the wavelength range, into this wavelength range. The thermal radiation includes the entire visible spectrum and the infrared radiation, as well as a portion of ultraviolet radiation. If you see this range, right? If you see this range from 0.1 to 100 micrometers, so it includes the infrared spectrum and the visible spectrum and the part of the ultraviolet spectrum. Now the black body radiations. A body at a temperature above absolute zero emits the radiation in all the directions over a wide range of wavelengths. The amount of radiation energy emitted from a surface at a given wavelength depends on the material of the body and the conditions of its surface, as well as the surface temperature. Therefore, different bodies may emit different amount of radiations per unit surface area, even when they are at the same temperatures. It is natural to be curious about the maximum amount of radiations that can be emitted by a surface at a given temperature. So the answer of this curiosity is given by the black body. So the definition of an idealized body called a black body to serve as a standard body against which the radiation properties of real surfaces may be compared. So from this comparison, we can just say that which body has the radiation which is near to the black body, and which body has the radiation emits the radiation near to the white body. So a black body is defined as a perfect emitter and absorber of radiation. So these are some features of a black body. So at a specified temperature and the wavelength, no surface can emit more energy than a black body. A black body absorbs all the incident radiation regardless of wavelength and direction. Also, a black body emits radiation energy uniformly in all the directions per unit normal to the direction of emission, as you can see in this diagram. A black body can emit the radiation uniformly in all the directions, whereas the real body emits the radiation in a non-uniform manner. So a black body is a diffuse emitter. What does it mean? Diffuse means independent of direction. Now let's discuss about the Stefan-Boltzmann law. The radiation energy emitted by a black body per unit time per unit surface area was determined by Joseph Stefan in 1879 experimentally, as given by this expression. This EB is called the black body emissive power, and this expression is known as the Stefan-Boltzmann law, where we can simplify this expression that the black body emissive power is directly proportional to the fourth power of the temperature. When we replace the proportionality sign and put the equality sign, we will put some constant, and this constant is known as the Stefan-Boltzmann constant, which has a specific value that is known as 5.67 multiplied 10 raised to the power minus 8 watt per meter square per k to the power 4. And here temperature is in absolute temperature of the surface. Here one thing is very important to note, that the emission of thermal radiation is proportional to the fourth power of the absolute temperature. This is represented by the units which is known as watt per meter square. A black body would appear black to the eye. A distinction should be made between the idealized black body and an ordinary black body surface. Any surface that absorbs the light, it may be the visible portion of the radiation, would appear black to the eye, and a surface that reflects it completely would appear the white surface. Considering that the visible radiation occupies a very narrow range of wavelength spectrum that ranges from 0.4 to 0.76 micrometer, we cannot make any judgment about the blackness of the surface on the basis of visual observations. Sometimes we have a radiation that lies outside this range, that is from 0.4 to 0.76 micrometers. That may be infrared, or that may be violet radiation. So we cannot see these radiations by our naked eye. So for example, snow and white paint reflects the light and thus appears white, but they are essentially black bodies for the infrared radiation, since they strongly absorb the long wavelength radiations. So this is the simplest phenomena. So the surface coated with the lamp black paint approaches idealized black body behavior for our considerations. So this is a picture, and this body is closely resembles to a black body, which is actually a large cavity with a small opening, right, as you can see in this diagram. So the radiations coming in through this opening of area A will undergo multiple reflections with the inner walls of this cavity, and it will have several chances to absorb by the interior surfaces of the cavity before it finally goes out from this small opening. So if the surface of the cavity is isothermal at the temperature T, so the radiation emitted by the interior surfaces, right, will stream through the opening after undergoing multiple reflections. So it will have a diffuse nature. What does it mean? So it will diffuse in all the directions independent to the particular direction. So it is independent to the direction. So it will emit in all the directions with same kind of magnitude. Therefore, the cavity will act as the perfect absorber and the perfect emitter. The opening will resemble a black body of a surface area A and the temperature T, regardless to the actual properties of the cavity, and this opening is simply known as the black body. So let's discuss about the Planck's law. Before going into details, let us see that this parameter which is known as EB, and we have just studied the Stefan-Boltzmann law, and that was given by the total black body emissive power was represented by this EB, and which was actually the sum of the radiations emitted all over the wavelengths. Sometimes we need to know that the spectral black body emissive power, this is one of the most important parameter, right? That the spectral black body emissive parameter, which is the sum of the radiations, the amount of radiations energy emitted by a black body at an absolute temperature T per unit time, per unit surface area, and per unit wavelength about the wavelength lambda. So this is a particular expression which was given by the Planck in 1901 in conjunction with his famous quantum theory, and in this expression these two C1 and C2 are the constant, and this lambda is known as the wavelength, and this T is known as the absolute temperature of the surface. This relationship is actually valid for a surface in a vacuum or a gas. So in this expression, this wavelength and the spectral black body emissive power has a relationship, and we will see a graph that will shows the variation of the spectral black body emissive power with the changing in wavelength. So this is what I have just read about the parameters which are mentioned in the previous equation, that is the Planck's law, and these are few points, and I will read these points for the upcoming graph. This is actually the graph which shows the variation of the spectral black body emissive power with the wavelength. We will try to understand this graph, that by changing the wavelength how the spectral black body emissive power will change, and we will see the effect of temperature, right? And we will see that what kind of radiations that we will see at the particular temperature, right? So the one thing is clear, that the radiations or the spectral black body emissive power or the emitted radiation is a continuous function of the wavelength. As the wavelength varies, the spectral black body emissive power will also change. So this graph has different curves for different temperatures, right? Different temperatures, let's say 100 Kelvin, 300 Kelvin, 500 Kelvin, and 1000, 2000, 4000, and 500, 5800 Kelvin, right? So we will select first one temperature curve, right? And then we will see that by changing the wavelength how the emissive power of a black body will change. Let's say we'll select this temperature, that 100 Kelvin, right? So if we increase the wavelength, right, the emissive power of a black body will increase up to a certain highest value, right? And at this point the wavelength would be somewhat around 50, right? And after that wavelength the emissive power of a black body will decrease. So at any specified temperature, the spectral black body emissive power will increase with the wavelength, which reaches at a peak value, and then it will start declining or decreasing with the increasing wavelength. So this is the first point that I have discussed, that for a given temperature, for a particular temperature, by increasing the wavelength, the emissive power will increase to a certain highest value, and then it will decrease for a particular black body. So the second point is, if we see that at a given value of the wavelength, right, if we fix the value of the wavelength, right, so let's say this is 0.1 and this is 0.5 and this is 1, and if we fix the value of the wavelength, then we will see that by increasing the temperature, the radiations emitted from a black body will also increases. Let's say this is a vertical line which touches over here with this 2000 Kelvin line. So at 2000 Kelvin line, so the emissive power will be just like here, right? And if we further increase the temperature from 2000 Kelvin to 4000 Kelvin, the emissive power will also increase from this value to this value, right? So it means that at a given value of the wavelength, right, if we increase the temperature of a black body, the emitted radiations will also increase, right, by increasing the temperature. So the third point is, as the temperature increases, when we see this whole diagram, right, as the temperature increases, the curves, these temperature curves will shift to the left side of the graph, and which is the region of the shorter wavelength, right? So by increasing the temperature, right, so from 100 to 300, 300 to 500 to 1000, so we are seeing that the increasing trend of the temperature will shift the curve on the left hand side of the graph, which is the region of the lower wavelength, right? So the larger fraction of the radiation is emitted at the shorter wavelength, right, at the higher temperature. For example, this is the lower temperature, right, and it will emit the radiation somewhat just like 10 raised to the power 4, right? So when we increase the temperature from 100 Kelvin to, let's say, 4000 Kelvin, so the two things will happen, right? So the wavelength will be smaller, right, and the energy of the radiations will be the higher. So the last and the fourth point is that the radiations emitted by the sun, which is considered a perfect black body at the temperature of 5780 Kelvin, or roughly 5800 Kelvin, right, reaches its peak in the visible region of the spectrum. So this is the visible region. This is the shortest region. So if the temperature is that much high, right, so we can see the visible spectrum or the radiations which are in the visible spectrum, right? Therefore, the sun is in tune with our eyes. On the other hand, the surfaces which are at the temperature of less than 800 Kelvin emits the radiation which are completely in the infrared region, and they are not visible to our eye and until or unless they reflect the light coming from the other sources. So the last point is this peak points of the temperature curves shows that when we increase the temperature, right, the peak points are shifting towards the shorter wavelength with the higher emissive power of a black body. So the next is the Wien's displacement law, and this says that the wavelength at which the peak occurs for a specified temperature is given by the displacement law. So what does this peak means? This is the peak value for a given temperature, right? So the wavelength at which the peak occurs for a specified temperature is given by the Wien's displacement law. So by using this expression, we can get the value of the wavelength if we put the temperature, right? So this is the graph which is given for the 100K, 300 Kelvin, 300 Kelvin for the specific value, right? And if we put the value of 100 Kelvin, right? So it will give the maximum value or the maximum or the peak value, and we will have the value of the wavelength that is approximately equal to 50 micrometer. So what if we need to put the temperature of 150 Kelvin. So there is no curve for the 150 Kelvin. So this is the law which basically used to put any kind of temperature to get the value of the wavelength and its peak for that particular temperature, right? So when we put the different temperatures, let's say 100 Kelvin, 300, 500, 1000 and 2000, we can plot the values of this Wien's displacement law, and we will have these peak points or the locus points of the radiation emission curve, which is basically shown here. So this is basically the example which shows that the peak of solar radiations that occurs around 5800 Kelvin. If we put the value of temperature 5800 Kelvin, we simplify that, we will have the value of the wavelength that will be equal to 0.50 micrometer, which is in between the range of visible spectrum. So the visible spectrum wavelength ranges from 0.4 to 0.76 micrometer. So this 0.50 is in between the range of visible spectrum. So we can see that from here, that if we put the value of 5800 Kelvin, so if we go down, so the wavelength value will be in between the visible spectrum. So similarly, we can get the value for the wavelength if we put the temperature, that is room temperature 25 degrees centigrade or 298 Kelvin, right? We can get the value of the wavelength, which is 9.72, and which is beyond the visible spectrum, right? And this is in the infrared region of the spectrum, which cannot be seen by the simple eye. So this is the diagram which actually shows that, so when the visible light falls on a particular object, so there will be the absorption of some wavelengths of radiation. Let's say the incident light has these four wavelengths of radiation, that is for the red color, yellow color, green and blue. So out of four, three of the colors wavelength like yellow, green and blue has been absorbed in this body, and only the red color wavelength is reflected. So we will see that this object will be in red color. And similar is the case when we see the leaves of a plant, that the sunlight falls on the leaves, we see them, the leaves are in green color. This is because of the chlorophyll, which actually absorb all the lights and only reflect or strongly reflect the green color and absorb all the remaining colors. So that's why we see that the leaves of a plant are green in nature. So let us take an example of the radiation emission from a black ball. Let me just read the question statement, which is: consider a 20 centimeter diameter of a spherical ball which is currently at the temperature of 800 Kelvin, and it is suspended in the air, as you can see in this diagram. Assuming the ball closely approximate a closed body, so we are assuming that this is a black body. So what you have to determine the total black body emissive power. Second, the total amount of radiations emitted by the ball in 5 minutes. And third point is the spectral black body emissive power at the wavelength of 3 meter. So let us just have a look on the solution, that an isothermal sphere is suspended in the air, and the total black body emissive power and the total radiation emitted in 5 minutes and the spectral black body emissive power at 3 millimeter are to be determined. There is some mistake in this value. This should be 3 micrometers, not 3 millimeters. So keep in mind that. We'll take few assumptions that ball behaves as a black body. First, we have to determine the emissive power of this black body, and which can be determined by the Stefan-Boltzmann law. And we know that the Stefan-Boltzmann law, we have just studied in the previous slide, that the emissive power is equal to the Stefan-Boltzmann law multiplied by the temperature to the power 4. This temperature must be in absolute scale, right, or in Kelvin scale. So this is the constant value which has already been given, and we'll put the temperature which is given in the question statement, and after simplifying that we will have the value which is equal to 23.2 kilowatt per meter square, which is the emissive power of this black body. And in other units we can say that the ball emits 23.2 kilojoule of energy in the form of electromagnetic radiations per second per meter square of the surface area of the ball. Now let us see the second point, in which we have to determine the total radiations emitted in 5 minutes. To determine the total radiations emitted in 5 minutes, what you have to do is, first you have to determine the surface area of the ball, which is simply determined by using this formula pi d square, and after putting the values, this will become the surface area of the spherical ball, and the temperature is given is 5 minutes. So we need to convert the 5 minute into seconds. So this is the conversion factor. So 5 minutes, we need to convert the minutes into seconds. So 1 minute is equal to 60 seconds. So minutes and minutes will be cancelled. 5 into 60, that will be equal to 300 seconds. So simply 5 minutes equal to 300 seconds. So by putting the value of the area and the time and multiplying it with the emissive power, we will have the total amount of radiations emitted from the black body or from this spherical ball in 5 minutes. So this is the value that we got in our previous part of the solution, that is 23.2 kilowatt per meter square, and if we multiply by the area, this area will cancel with this area, and if we convert the kilowatt units, kilo means 1000, and if we convert it into kilojoules, this will be the conversion factor, right? So this delta T is mentioned over here, 300, and this part which is in the bigger parenthesis, which is simply known as the conversion factor. So for conversion factor for this kilowatt, this is kilowatt, it can be written as 1000 watt. 1000 watt is equal to 1 kilojoule per second, right? And second will be cancelled out. This watt and this watt will be cancelled out. This kilowatt will be cancelled out. We will have simply at the end kilojoule. So the total amount of radiations which are emitted from this spherical ball or the black body in 5 minutes is equal to 876 kilojoule. So the third part is to determine the spectral black body emissive power at a wavelength of 3 micrometer, and it can be determined by the Planck's distribution law or the Planck's law, and this is the formula that we have just studied in the previous slide. You just have to put the value of this 3 micrometer wavelength over here and over here, and the temperature is 800 Kelvin. The remaining C1 and C2 are the constants, and the values can be put in this formula, and after simplifying that, the spectral black body emissive power will be 3848, and it means 3848 watt per meter square per micrometer.